We're going to just look at comparing things from one side. And by one side, we're meaning either the zero side of things or the infinity side of things on a number line. Okay. And this is going to lead into something called the one-sided limit comparison test. So first of all, we have this, our limit comparison, an over bn. And if this ratio comes to a limit L, they're going to behave the same. And the first example I've given here is when the denominator is small and converging. So the bn is small and converging, then this ratio, if there's a limit, they behave the same, so they're both converging. Okay, so it's their limit test. Now we're going to look at this from one side. If the an is being compared to a bn, and the bn is small and converging, and it converges to zero, so the limit is going to zero. What that means is, from one side, the zero side, the an must be smaller. Okay, so I'm just going to write this in. So this must be, the an must be smaller. Okay, and then we can make this the assumption if an is smaller and bn is converging, then we can say that it must also be converging, smaller and converging. Okay, now this only works for one side, the zero side, because if we look at it from the other side, so we have a bn in the bottom that's small and converging, and the an happens to be larger, so our limit becomes infinite. Okay, so our limit is becoming infinite here. Well, that's inconclusive. It's because we know that it's small and converging, the bn in the denominator. The an is larger, but if it's larger than converging, we don't know if it's going to still converge or it's going to go to infinity, so it's inconclusive. So this is what we call a one-sided test. Okay, we're only testing it from one side. In this case, the zero side, when we have a small converging in the denominator. If we look at from the other side, though, we can make some other different conclusions. So again, here's our limit comparison. If an over bn is a limit, then it behaves like the denominator function. So if we then, instead of having a smaller converging denominator, we can test it against a larger diverging denominator. So if that's the case, if the denominator is diverging, we know that the an at a limit must also be diverging. They behave the same. Okay, what happens if we have an an over bn over a large diverging bn, and the limit is infinite? Okay, what does that tell us about the an? Well, it must be that the an is larger, and if it's larger than a diverging series, it must also diverge. So we can make this argument from the infinite side, so the one-sided being the infinity side, and we can make this conclusion if we're talking about a large diverging denominator. Okay, just like we could make it from the zero side for a small converging denominator. If it happens that we have a large diverging denominator and the an happens to be smaller and goes to zero, okay, well, what does that mean? It just means that we have the an is smaller. It's smaller than a diverging sum, but just because it's smaller than infinity, it doesn't mean that it has a finite sum. So in this case, on the other side, this is inconclusive. The smaller over large diverging going to zero is inconclusive. However, from one side, the an over large diverging going to infinity means that an is even bigger, which means it's diverging. It's larger, therefore diverging. So this is how we compare things from one side. And leads into the one-sided limit comparison test. So the one-sided limit comparison test says that if we want to show that an is convergent, Okay, if we want to show that AN is convergent, we need to choose a BN that is also convergent. So this is going to be this situation here. We want to show that AN is converging. And we can do that from the left side then. Okay, so we need a small converging function in the denominator. So that's why we need a BN that is convergent. And when we test the limit of AN over BN and it equals zeros, we can conclude that they both converge. And the reason is, if the limit is zero, that means that AN is decreasing faster than BN. AN is smaller, and since BN converges, AN must also converge. They must both converge. AN converges faster, they must both converge. So that is a one-sided limit from the zero side, and we need a converging comparison to do that. Now, there is this other situation as well. If we want to compare a one-sided on the infinite side or the infinity side, we need a large diverging series in the denominator, and we can test it from one side only then. So to show that if AN is divergent, the series for AN is divergent, we need to choose a BN that is also divergent. And if we can show that this limit of AN over BN, that ratio tends to infinity, that means that AN is bigger than BN. BN is divergent. The series BN is divergent, so the series AN must also be divergent. They both diverge. AN is increasing faster than BN, so they both diverge. In fact, AN diverges faster, but regardless of faster, they both diverge. So we're going to summarize this in this table. In the red is our limit comparison test, okay, when we actually get a limit, a non-zero limit. AN over BN, going to the limit, they behave the same, they both converge. Okay, if the known function BN converges, they both converge. If the known BN diverges, they both diverge. They just behave the same. And that would be the case in the middle here, what I've highlighted in yellow here and here. This is our limit comparison test. The one-sided limits are in green here. And if we're going to test the one-sided limit at zero, we need a BN that converges. Okay, we need a BN that converges. If BN converges and AN over BN goes to zero, that means that AN is less than BN, they both must converge. If we test it at the other side though, okay, AN, if BN diverges and it goes to zero, it just means that AN is smaller than BN, but it just means that AN sum is less than infinity, but less than infinity could also be infinity. So it's inconclusive from that side. And then on the infinity side, okay, if we're talking about the infinity side here, then we want to use a diverging BN. And if AN over BN is infinite, means that AN is bigger than a diverging series, they both diverge. In fact, AN diverges faster. Okay, so we can make some conclusions. However, if we test it on the other side, okay, BN is converging and AN over BN is infinite, okay, well that means that AN is bigger than a converging series. Well, bigger than a converging series could be converging, it could still be infinite, okay, based on this result here. So it's inconclusive. Okay, so if BN converges, we can't test it from the left side. We can't test it from the zero side. Okay, so this is the summary of our one-sided test, and it's good kind of visual here to understand which series we can test on which side. So we can test converging series on the zero side in the denominator. We can test the diverging series in the denominator on the infinite side and make the conclusion that both diverge. On the zero side, we can say that they both converge. Okay, so this is testing from one side, and it depends on what you're testing in the denominator in both cases, because if it's going to zero, here with a small converging and going to zero with a large diverging, We can make conclusions in one and no conclusion in the other.